let's look at the so-called man-in-the-middle attacks. Technically, any type of attack in which a third party manages to get between the two original parties that are communicating is referred to as a man-in-the-middle attack. And we often abbreviate this MITM. MITM is often accomplished by ARP spoofing. By ARP spoofing, we mean manipulating the MAC addresses stored in the ARP cache of the communicating computers, and I'm going to show you how this works. A little refresher first about ARP and the usage of ARP. Remember, even though IP numbers are used to move packets across the Internet, the destination MAC address, MAC stands, of course, for the Media Access Control Address. This is often referred to as the hardware address of the network interface, or the physical interface is another way of referring to this. At any rate, you need the destination Media Access Control Address before you can send a packet, and this is put into the frame header. So we have a protocol called ARP, abbreviated ARP, stands for Address Resolution Protocol. Whenever a MAC address is needed, the ARP protocol will broadcast a request for the MAC address of the device with a particular IP address. We'll see how this works in a moment. The device that is using that IP number will respond with its MAC address back to the requester. The requesting device uses that MAC address as the destination address in the frame header. I mentioned that a couple slides ago. The frame header of the packet, and also places the IP number and its MAC address in its ARP cache, where it will stay until it times out and is flushed. The reason for this is if the requesting computer needs to communicate again with that computer within the next couple of 3 minutes. It depends from the timeout period depends on the operating system. But if the requesting computer needs to continue communicating with the destination computer for a period of time, since the mapping of the IP number to the MAC address is going to be stored in the ARP cache of the requesting machine, it will not have to issue another broadcast ARP. This is going to serve to minimize network traffic. If memory serves me well, on a Windows machine, I think entries are stored in the ARP cache for 2 minutes if they aren't used again, and if they're used in that 2-minute time, the timeout period is extended 8 more minutes to a total of 10 minutes. And the reason these things aren't permanently stored somewhere is the fact that it's possible for example, if you're using DHCP, it's possible for a computer when it boots up to get a different IP number today than it had last week, for example. So if you had static mappings of these things, that would be incorrect. So ARP is an example of what I consider a dynamic protocol mechanism whereby things can change on the Internet, and we as network operators do not have to go in and change static tables. The automatic dynamic protocols take care of this for us. But as you see, this comes with a cost. Okay, what can go wrong here? In the process, if a packet needs to be sent, the ARP cache is checked first for the needed MAC address. When the ARP is implemented on any device in the TCP/IP stack, some decisions have to be made. Most devices are written to where they will accept something called a gratuitous ARP. Now, a gratuitous ARP is an unsolicited ARP announcement, and it has legitimate uses on the network, but it can be used to fool other devices into loading erroneous IP to MAC mappings into their ARP cache. Up here I say most devices will accept a spoofed gratuitous ARP. Anytime you see the word spoof, you can think, okay, somebody is lying, pretending to be something they're not. So the way a gratuitous ARP works, if your computer is sitting there minding its own business on the network, and another computer sends it an ARP packet that says basically IP number XYZ is at this particular MAC address, your computer will very happily take that information and put it in its ARP cache. So there was no request sent out for this information, but if the ARP packet shows up at your computer will very happily take the information. It was originally considered to be a way to speed up the whole process. You know, whenever your computer gets a chance to learn a new MAC to IP address mapping, it should take advantage of it. And we'll see what the implications of this is. So why is this a problem? Since the destination MAC address is used by the network interfaces to determine which interface should respond to a packet, and it's also used by modern network switches to determine which interface gets to see the packet, a packet with the wrong destination MAC address will be processed by the wrong destination. And I've got some drawings here to show you why this is a problem. So this is my first graphic, and let's see what we have here. We have this one has 3 computers. This is the router. I forgot to mark that. In the first 2 or 3 slides here, the router has in place no part. This is a switch. So we have 3 computers, and let's assume here that this computer at 192.168.100.25 has a MAC address of AA, and again I've just abbreviated this to keep from having to write a long genuine MAC address. Now let's assume here that this computer, the .25 computer, has a packet that needs to be sent to 192.168.100.90. Now this is on the same network. So the source IP is going to be the .25 machine. The destination is the .90 machine. The source MAC address is the AA. Now, at this point, unless it's already in the cache, the .25 machine doesn't know the destination MAC address of the .90 machine. So what it does, it sends out an ARP request, basically asking who has 192.168.100.90, and this is a broadcast. So this packet is going to go into here, and it's going to go to here, and it's going to go down to here to the router, and it's going to go up to here. Now, the .90 machine is the one that actually has, obviously, is using this particular IP address that's in the ARP request, so it's going to send a reply. Okay, the reply goes back over to here. So at this point, this original computer here now can fill in this destination MAC address, and the packet can be sent. This is the way it's supposed to work. Now, let's look at a situation where our gratuitous ARP can be used to redirect the traffic, or to direct the traffic. I don't like the word redirect in this case, because you might get it confused with another type of attack. But let's assume in this case we got the same players we had before. But now at some point before the .25 machine wants to send a packet, the .50 machine, where the attacker is sitting, is going to send a gratuitous ARP to the .25 machine saying the .90 machine is at BBBB, and the .25 machine will put this in its ARP cache. The ARP cache is just held in memory on the particular computer, and I'll abbreviate this. .90 is at BB BB BB, and the attacking machine has to keep this up. If the ARP cache entry is going to time out in 2 minutes, the attacker is going to send this packet on a frequency less than 2 minutes, just to keep the make sure there's always this entry in the ARP cache of the .25 machine. So at this point, if the .25 machine needs to send something to .90, it's going to look in its ARP cache before it sends the packet. It's going to discover that it already has an entry in the ARP cache, and that the .90 machine has a MAC address of BBBBBB. So it's going to use this to address the frame header. So when this packet is sent, it's going to go to the switch, of course, and the switch is going to look in its switch table and notice that BBBB is on port 2, and it's going to send the packet out to port 2. So the packet is actually going to go directly to the .50 machine. Now never mind that we've got it, the IP address is .90. By manipulating the MAC addresses, the packet is actually going to be sent over here to the .50 machine, because the .50 machine has the MAC address that the original sending computer found in its ARP cache that corresponds to .90. Now, usually what happens here with this particular type of attack, this machine here is set up to do IP forwarding. IP forwarding. And this is an interesting thing that's built into a lot of operating systems. For example, all the Windows operating systems have this. You have to turn on the registry, but it's not hard. And what IP forwarding does is, once this packet comes in, the operating system is going to realize it's going to do its own check on this, and it's see, this machine hasn't been spoofed. It really knows where the .90 machine is. It's going to readdress the packet and send it back to .90. So let's put this down here. Readdress packet with the correct destination MAC and send it back out. So the original destination computer is going to get the packet. Now it's been I guess you could call this rerouted through the attacker's machine, or the man in the middle. Now, Usually what happens here is while the packet, is in this machine, it is sniffed. And hopefully everybody knows what sniffing is by now. The packet's going to be sniffed. And it's actually possible in certain situations that the packet could be changed, depending on what the contents of the packet are. So here you have your basic man-in-the-middle attack. Let me go over this again. A gratuitous ARP is sent, and the receiving computer puts that entry into its ARP cache. This is also called ARP cache poisoning. So now we have an incorrect or spoofed entry in the ARP cache of a computer. If that computer needs to send a packet, it's going to look at its ARP cache first. And in this case, it's going to find an incorrect entry, but it doesn't know that and has no way to check it. So it will send the packet with an incorrect MAC address. Notice the switch switches the traffic based on just the MAC address. So in this case, when the packet arrives at the switch with the destination address of BB, it's going to be sent out port 2. It's never going to be sent to what we would consider the correct address based on the IP by the switch, because the only thing the switch is looking at is layer 2 information, which is found in the frame header, basically source and destination MAC address. So this is your basic man-in-the-middle attack. To get the return traffic directed back to the man-in-the-middle, it's simply a process of doing the same thing in the other direction. We're going to tell, in this case, we're going to tell the other computer that the .25 machine is at BBBB. So this is going to go through the switch over here to this machine. And again, this machine is now going to put this into its ARP cache. And again, I'll abbreviate. So any return traffic that's destined for .25 is going to be sent to MAC address BBBB, because that's what's in the ARP cache when the packet needs to go out. Now again, these packets need to be sent frequently enough that the ARP cache always has this entry in it. So the return packet here, all this right here, is going to be sent to the switch, and the switch is going to note the destination MAC address and say, okay, that's on port number 2, so it's going to go through here and again come down to here, and as before we have IP forwarding. Enable, so the packet's going to be readdressed, sent back to the switch, and by the switch it's going to be sent back to the computer that originally should have gotten the packet. And again, while it's down here, we have a sniffer, etc. So in this case, by sending out gratuitous ARPs to both ends of the conversation, we can actually direct traffic in both directions through our machine, or the attacker can do this. Now, these examples have looked at traffic on the local network. It's no harder to do it on traffic that's going out to the internet. So here we go again. Now in this case we're going to send a packet to, I just wrote down the IP number at the college, 216.69.9.15. It doesn't matter what this is. The fact is it's different. It's on a different subnet than the sending computer. And if you remember your networking, in this case the source and destination IP numbers are going to be used, but the destination MAC here in this case is going to be this is the MAC of the default gateway. And of course we all know this is actually the router. So when the packet needs to be sent out, this computer, the .25 computer, is going to realize that the destination is on a different subnet. So the ARP request that's sent out is actually who has 192.168.1.100. This is the, in my example here, the default gateway. Now again, this is a broadcast, so the packet, this particular ARP request is going to go to everything that's hooked up to this switch. However, the only device that's going to respond to this is the one that actually has that address. And so this is the reply. This is from the router. It's going back to the original machine, and again this is going to be put in the ARP cache. .1 is at cc.cc-cc. And in this case, after this ARP reply, the packet can be properly addressed and sent. Now, this is what usually happens. Same process as we had on the local network. To circumvent this, the attacking machine here sends a gratuitous ARP to this machine. Actually, I could do this, send this to many machines, but we're telling the .25 machine that the .1 machine is actually at BBBBBB. And again, this is put in the ARP cache. So the next time the .25 machine needs to send something through the default gateway out to another network, it's going to look in its ARP cache and find out that .1, the default gateway, is at BBBBBB. So this actual packet here, again, is going to be sent to the switch. The switch is going to say, well, okay, this goes to MAC address BBBBBB, which is on port 2. So just like before, we have this machine set up to do IP forwarding. It's going to properly address this packet, send it back through the switch, and the switch is going to realize that where it really needs to go, based on the correct MAC address, is to port 3 in the router, and then the router is going to decide it needs to go on out to the internet. It's the same process as what we had a while ago, except in this case the packet's going to wind up at the router. It's eventually going to wind up at the router and be sent on out onto the internet and the proper destination. But again, it has gone through this attacking machine, which could be running a sniffer, or potentially modifying the contents of the packet. To manipulate the return traffic, all we have to do is send another ARP. This gratuitous ARP says .25 is at BBBB, and it's going to be sent through the switch to the router. And of course the router maintains its own ARP cache. So the ARP cache, that's a P, ARP cache of the router now will have the entry 25 is at BB, BB, BB. When the destination traffic comes back from the internet, in this case the 9.15 machine, notice the destination IP is to the .25 machine. The router is going to look up in its ARP cache and find an entry for .25, that being BBBBBB, and it's going to properly, well, not properly, but it's going to address the packet with BBBBBB. So this packet is going to be sent through the router and again down to the attacker, which of course has IP forwarding turned on. This machine knows what's going on, knows that the .25 machine is really is at AA. It's going to readdress the packet after it sniffs it and or modifies it. Isn't going to send it to its final destination. So if you think about this, what happens? The packet winds up where it's supposed to go, but it passes through another computer. Now, you might be sitting here thinking, well, there are some protocols that are set up to prevent this from happening or make it detectable when it happens. For example, there's something called the secure SSH, excuse me, it's SSL, secure sockets layer. And the secure sockets layer is typically what's used on the internet whenever you go to a site and do some sort of electronic commerce. If the site has HTTPS as part of its URL, it's using the secure sockets layer protocol. Actually, the secure sockets layer is kind of morphed into something called TLS, or the transport layer security. In this case, what's going on is there's and I'll do a little video on this. There's an exchange of a public key, which is a large number used in cryptography. The public key is sent to the client computer, the requesting computer. The requesting computer uses the public key of the server to encrypt a session key, which is the key that the number is actually going to be used for the encryption process. And it sends this encrypted session key back to the server. The server has something called private key that corresponds to the public key that it sent to the requesting computer. The server uses its private key to decrypt the session key, and at this point both ends of the transaction have an encrypted session key known only to them. This is how it works. Now, the thing about the man-in-the-middle attack is that the man in the middle could send its own public key to the victim. So the attacker is basically setting up an SSL session between itself and the web server, and it's also setting up one between itself and the victim. Now, the victim's computer, when it receives this public key, it's going to receive it in something called a certificate. The victim's machine was going to realize that there's something wrong with the certificate, and it will show a an error message on the screen inside Internet Explorer, for example. It'll basically say there's something wrong with the certificate. Maybe the name doesn't match. Because remember, it's a spoofed certificate. Okay? And so you get this error message on your screen. Now, what do most people do? Do they say, okay, there's something wrong, I better stop what I'm doing? Of course not. Most people will say, I just want to do what I set out to do. I don't want to look at error messages. I don't want to think about what's going on here. So most of the time, the victim will just click on OK, accept the certificate. So now you're still using SSL/TLS. But now you have two sessions going on. There's one between the victim and the attacker. There's another one between the attacker and the original destination website. So the victim thinks he's communicating with the destination website, when in fact the man in the middle is looking at the traffic each way, and while it's on his computer, the attacker gets to see unencrypted information and can recover such things as bank passwords, account numbers, all kinds of interesting information. And if you're sitting there thinking that this is going to be kind of tricky to do, actually it's not that hard. I can basically go to your bank, download all the bank's pages. I can set up a little mini web server on my computer and make you think you are connected to your bank while you're completing your transaction that I'm looking at, and then passing on to your real bank website. And there are tools that help you do this that have been developed by, well, I'm sure there's bad guy tools, but there's actually tools that have been developed by people that we think are on our side. You are interested in this, you should do a little research on this. You could do a Google search on man-in-the-middle tools, or you could Google up a guy named Doug Song, who's done some interesting things. One of his main tools is called DSNF, which will actually, it's a whole suite of tools actually. It has a number of things that will help you do these type of attacks. So what can you do about this? See, what I consider the unfortunate thing about these types of attacks is the attacker is using the protocol against you, the protocol and the implementation of the protocols. In this case, where the whole attack is based on the fact that most computers have been programmed to accept gratuitous ARPs. And as I mentioned earlier, there are legitimate uses for this. If you're really interested about want some more information about gratuitous ARPs, you can Google search on that too. But the attackers have studied the protocols and studied how things are usually implemented, and discovered that there's a way to use this against us. So what can we do about this? You could add a static ARP entry for the default gateway using ARP-S, which stands for static, on each computer. Now that's going to take a little time, but it is a solution. There are also tools and intrusion detection systems, or IDSs, that monitor IP to MAC mappings and will alert you when a mapping changes. So this is basically you need to start with some sort of database, or in case of IDSs, they actually learn as they go. They all these tools. basically all these tools need to be someplace where they need to be listening somewhere they can see all the traffic. And every time they see a packet like an ARP request, an ARP reply, they make a note of the IP number to MAC address mapping. And if they've got an entry in their little database and they see a different entry for that IP number, different MAC address, they send out an alert to you saying, this has been changed. And it could be legitimate, like I mentioned earlier. If you're using DHCP and a computer reboots, it might get a different number than it got last time. Now they tend to get the same number, but they don't have to. So those are a couple of things you can do about this. One of the unfortunate things about these attacks that utilize weaknesses in the protocol is that sometimes it's not that easy to come up with a mechanism that will thwart the attack but not break the way we do things.